Okay, should we start maybe? Anyone waiting over there? No. So I am Mattias. I work at PingCAP on the TiDB database, together with Daniel here, for example. Previously, I worked at MySQL. I worked at Booking. And yeah, now I'm working with databases again at PingCAP. And what I'm going to talk about is online schema change in TiDB and a bit in general as well. So what schema changes? Well, basically alter table, create table, indexes, any type of object more or less in a database. And as a generic, I would probably talk more about transactional databases. So more focused on smaller transactions, a bit more in scale and so on. I will come back a bit to what TiDB and so on as well. But the first part is actually quite generic, especially in the distributed manner. So it is a bit different if you're working on a single machine and does something versus if you have a distributed system with many machines and does something, because then you can't just take a lock of the whole system at once. That's much simpler in a single machine, for example. Reason for changing tables or anything, you most likely know that. New features, new use cases, missing columns, but it's also a lot of cleanups and so on, because development just progresses and something you need to remove and make sure that it's clean and lean. For better performance, etc. as well, adding indexes to a relational database, it's a quite common practice to do every now and then, depending on. Sometimes you should actually remove them as well when they're not needed. But it's quite easy, right? Because it works on my machine, so we can just ship it. That's quite easy in a developer situation. But in a developer environment, it's usually much smaller scale, both data-wise. You don't have any concurrency usually by other, even other versions of the application, because when you're deploying applications, often you're actually running multiple versions of the same application at once, etc. What else? Disk sizes. You usually have less disk, you have more disk available, etc. as well. Often you do have some kind of replication going. If you have a single node system and replicate for example, Postgres or MySQL, then depending if it's a logical or physical replication, if it's logical replication, then it actually doesn't start the schema change on the replica until the prior is done often, which can lead to quite long replication delay, etc., which then forces things on the application to handle instead. So normally the biggest issue with schema changes, it will start to block something, right? And that's, you can't just block a database in a production system, because then you're basically done. Early days, the simplest way to implement the schema changes was basically take a lock on the whole object, do the changes, and then release the lock, basically. Part of that, it might be that the alter is transactional or atomic, at least. And actually, buying back a bit to the previous talk, is it actually necessary to be have a full lock, so you have all the transactions before the metadata, before the change, to see one version, and then you do the change atomically, and then all new transactions will see the new schema or the new column or whatever you do. I would like to challenge this a bit. So I would say that the data should actually be fully transactional, right? Fully consistent. But does the schema really need to be that? Is it okay to have a column that actually one transaction can see and another transaction don't see? No objections?
If you are adding columns, just by removing it.
Sorry?
If you are adding a column, just by removing it.
Yeah, anything really.
The application is looking for it.
Yeah, so you need to make the application aware of it, but the application needs to be aware of it anyway. Does it matter that one transaction of the application sees one version and another sees another version, because you will not roll out the application at the same time as the schema changes is done, right? So the application should be handled anyway.
It depends if you keep running the older version and just ignore the column until you enable the feature flag.
Yep.
You know it's there, it's fine.
Yep.
No.
Adding is all right, but removing usually is.
Yeah, but that doesn't really matter if you just loosen the concept of blocking the transactions before and after the schema change is complete. So that's the whole idea, actually, that if we remove that, we allow that two different clients sees different version of the table still at the same time. They see the same data, but they might see with an index or without an index, or with a new column or without a new column.
I'm sorry, I don't understand why at the same point in time, how can there be a column and not?
In a distributed system,
Okay.
for example, or that just you have two different transactions, right? You will probably have two different snapshots anyway.
Because one was started before.
Yeah. And most, and especially in single node databases, what you do is at least you take a metadata lock. So you need to make sure that all transactions that already started before the metadata lock finishes before you can start any new transactions. And even if you have a very small schema change, like a metadata schema change only, it still would block transactions. So that makes it be a hiccup, and depending on how many transactions and dependencies you have, that might actually even be a big problem in production. So I would bind it slightly to how application rollout works. That's also, you don't just shut down all the applications, waiting until they're done, and then you start a new application, right? So if you have that mindset also for the schema changes, it makes more sense and makes it easier to remove even these small hiccups where you have a blockage between transactions before and after the change. So if we allow that, then we can actually do non-blocking alters. So what you do is you're versioning the schemas globally. So yeah, again, in a distributed system, you can of course do the same in a single node machine, but it's more important when it's distributed, because you don't want to stop the whole distributed database for doing a single change. Then you split the alter into smaller stages where you allow the current state to be backwards compatible with the previous state. Then you can move the states one by one and let the current running transactions more or less continue to live and die without blocking them. What else? That also means that you can actually tune it a bit as well if you want to focus on forcing the schema change as fast as possible. So if there's long running transactions, you can actually kill them more or less, or make them roll back. Or if you know that our transactions are quite long, so we're focusing and want to prioritize them, let the DDL take a bit longer time then. So as an example, let's create an index. What we do is actually from a paper by Google, Online Schema Transactions in Spanner F1, I think it is. I have a link on it later. We can split it into several different states. So state none, that's when the index doesn't exist. Then there's a weird state, delete only, by delete only when there's nothing. I'll come back to that one. Write only, so you're updating the index with whatever you have. Then comes the big part, that's the write reorganization, where you read all existing rows and backfilling the index. And this is normally what takes a long time. If it's a big table, of course, you need to read all the rows, or well, the column from that table, and sort them, create the index, etc. when that's done, you can actually make it public. So now the index exists and can be used by new transactions as well for searching, for reading. So then the delete only, well, the index didn't exist, right? So coming from state none, yeah, that's not an issue because there's nothing to do, right? The problem is the next state then. So the write only, if you have a transaction in write only and it inserts a new row, then what happens with the transaction that's not in write only? So the previous state, if it was state none, then it would leave orphaned entries. So basically, if you have a small tables to start with, you would be in the write only, and you add a row, you add an index entry as well. And then in the state before, it might actually start a new transaction, but see the state before, right? Because it's a distributed system, things are a bit asynchronous within the different states. If it would be in state none, then it would just leave the entry and you would have an inconsistency in the index, right? So that's why there's a delete-only state. So it's actually to be forward compatible with the write-only state. Any questions around that? Okay, cool. So the whole matrix more or less goes from start to finish. And it's kind of easy with the compatibility between the different states actually to go from when it's all done and then backward to see a bit what you can remove and not. So you would start with removing select access to it. And then you can backfill all the data. The states here are the same, but it needs to be a border in between because otherwise there's race conditions with the backfilling. And then you do have the delete only, which more or less is only there to be forward compatible with the write only. So the weird part here is an update will actually be a delete only part of the update. So it will not fill in new index entries, but delete them only. And then you will have the start state.
Is write only then not the right name? Because write only implies it's also deleted.
Yeah, it deletes as well.
So maybe the only word write is maybe it should just be the right place.
Yeah, so what mean with the write only, it doesn't read from it.
Yeah.
So yeah, naming is hard.
It is.
So that is how one can implement a non-blocking schema change in especially distributed database. TiDB does this. I think Cockroach do more or less the same, different implementation, but the same inspiration. If it's done properly, then you can actually do this without even small hiccups due to metadata changes or anything like that. But to the expense that logically it might challenge you a bit that one transaction might not see what another transaction that starts after that logically should see the same thing. Then that's all the theory, right? But how can we use it and test it in production, etc.? And specifically, how can we make it fast and efficient? It's also a bit similar to the previous talk that we don't really need to do everything within transactions in the backfill phase, for example. But if you're breaking it down, there's several things where the biggest part from the beginning is the whole reorganization of data. So reading the existing rows, sorting it, as well as writing it again. That's where, for big tables, the majority of time takes. But there's also other things like processing these. We have customers that runs millions of tables, for example, in a multi-tenancy environment. And just bootstrapping that and creating a million tables, that can take quite a long time if the processing is slow. So there's several different ways of doing this. Something that we've done lately is actually handling the physical files and so on in a different way as well. We'll come into that. How many knows about TiDB here, by the way? Oh, cool to see. Then for the rest of you, I'll just go through it slightly, what TiDB is in design. It's built to be an online transactional database, but it has some features for lighter analytics and so on as well. It divides it in 3 different node types. You have a component, a compute layer, the SQL layer. What we have done is to re-implement the MySQL protocol, so it looks just like a MySQL server when you're connecting to it. So we're also supporting the MySQL syntax, etc. And then, of course, we do have our own, re-implemented both the protocol and parser and so on. And then we have our own optimizer, our own distributed execution engine, etc. And these are completely stateless, so it's very fast for spinning up new nodes or removing them, so it's a very elastic layer. It gets the metadata and some configuration from the placement driver cluster, and then the actual data from the row store, or optionally actually from a column store.
The question is that, do users decide where the data lives, whether it's the row store, the column store, is the same data?
The same data will be in both. So this is the default. The row store is default. We always store the data there. Then you can, by table, say how many copies you want in a columnar store. So that's completely optional. And that's per table, yeah.
How does the execution work? Is it vectorized, or are you going tuple by tuple?
It is logically tuple by tuple, but the internal protocol here is actually storing them in a more like vectorized, so it's a column by column in packages instead. So when we do some of the processing, actually internally column by column, but logically it's by row. Well, it depends. If we push down something to the column store, then of course it's columnar. So the row store, it's based on an LSM tree. What we released, if you're running it in open source or the current state, more or less, that would be RocksDB, which is a well-tested LSM tree implementation. We're using a raft protocol to keep data in sync. So by default, we have 3 copies of the data. Let's see if something else about that, how we can take that later on. That case. And since we do use the raft protocol for distributing data here, it was actually quite easy to also use the same raft protocol to stream the data to a columnar store, if it's configured for that table. And that's also some data merge tree, I think. And what we actually do as well is we're including the transaction timestamp. So it's actually completely transactional as well. So you see the same state of the database, regardless if the optimizer chooses a row store or column store. And it can actually mix and match in the same query, even. It's up to the optimizer to choose what's most efficient for this query. So if it's a big scan, for example, on a single column, it would use the columnar store. If it uses an index lookup or something like that, then it would most likely be the row store. And then we do have the placement data cluster. It has several functions. One is the PSS timestamp oracle. So that's how we're handling the MVCC. By timestamping at the start and then at commit time. The name placement driver comes really from organizing the data and distributing the data where data should go. We distribute data by ranges, around 100, 200 megabyte ranges. What the placement driver does is it monitors the storage. And whenever there's an imbalance, not only by size, but also by load, so both read load and write load, it will start moving these data ranges around, still making sure that it is in the different availability zones or something like that, so keeping the high availability properties of it, but also making sure that it's in well balance, so it can actually be highly utilizing the whole storage cluster.
Another question.
Yeah.
How is the placement driver layer? Is it also highly available?
Yeah. So if anything goes down, it will fail over. I think it actually uses an etcd storage as well for sharing some of the states when it doesn't store it directly in the row store. So yeah, that's also something that is quite good in TiDB, that when even placement driver node fails, the failover is quite fast, as well as it's stable directly. We see in comparison with other databases where it took a bit longer time, but also once it was failed over to another node, it was a bit shaky in performance until it stabilized. So then back to the DDL system. I'm not going to go in great detail by this. The point with the first implementation is that we used small transactions for just reading the rows, extracting the columns for the index, writing it down as to the index, to the new index, basically. And this was very stable, worked easy, was well tested and so on. But it was a bit slow, actually, because it's, yeah, new transactions. You need to take some lock internally and so on when you're writing to make sure that there's no collisions and so on. And it was slower than competitors. So what we did to take the big reorganization to read everything, sort it, and then write it, since we're using RocksDB or an LSM tree, we can actually do this in an offline version. You can even put it into new nodes that's not used for serving frontline usage. So you can actually do very efficient reads, do sorting, and then you can actually write it directly to your own LSM tree, so you're directly to SSD files, which means that then you can just present these SSD files to the RocksDB instance, ingest them directly, so you bypassed all the transaction layers and everything like that, which makes it very efficient.
Just to optimize the computation layer.
Sorry?
Just to optimize the computational layer.
Yeah, so both you can do it much more efficient in terms of reading. One way where actually before I think we even did like key value reads from the storage, and now we're using distributed coprocessor calls. So we're pushing down the filtering and so on, just returning the columns in an efficient way. So the reads are faster. The sorting and so on, you can offload that to new nodes, for example. So you can scale the cluster out to only handle DDL, for example, if you want. And then the biggest benefit is really the writing part, because then you skip all the transaction handling. You don't need to start more transaction for that. And then, of course, since this is done concurrently with the other load, we do have a temporary index that handles the concurrent writes and changes, right? So that's something like this. Since it's a temporary index, it actually needs to have some kind of tombstones as well. So when you're in the merge phase of the reorganization that it can be checked if it existed something in the new index or not, for example. So with that, it made the whole reorganization part quite efficient, but then we still had other parts that we profiled and improved for making sure that the full processing part went quite much better. I'm not sure we need to go through that in detail. The result is this more or less. And Lightning here, that's our internal name for ingesting files directly to the key value store. So all in all, I think this made the create index around 10 times faster, which meant that instead of being maybe 3 times slower than the competitor that we were comparing to, we were 3 times faster or slightly faster than them. But it also worked really well during high concurrent load. So since we're offloading this, it doesn't affect the day-to-day load. I think this actually was done like 3 years ago, and by then we had some internal benchmark, so it handles at least 1 million rows per second.
Mattias,
Yeah.
once you have the offline thing, if you want to replicate it, how does that work?
So you can,
Copies?
yeah, so you ingest the files and more or less, I think, if I remember correctly, that the instance you're ingesting it to will distribute it through the RAF protocol if done. Otherwise, I don't really recall the exact details there, but
Yeah, you can check the files.
Okay.
So that is unuseful.
In Postgres, for example, if you have non-log tables, and to log it, it's not possible. I mean, it's sort of has to write the whole thing.
Yeah, and that's one of the good things with an LSM tree, because the actual files are immutable. So, and then we do have the other use case with creating 1 million tables, where it doesn't really help to just be fast in creating the index, right? What we did there was also do a lot of profiling and changing the design and so on. In total, we were somewhere between 20 to 50 times faster after we'd gone through all this work. And this must be around 1.5 to 2 years ago we finished this. And that the main part here was how we do queuing of different nodes and so on, of different changes. We will not create a new schema version for each and every new table. We can group them together for one schema version. So since they are per table and so on, they're compatible still.
Can I ask about the use case?
Yeah.
Why they need like just curiosity.
Yeah, no, it's in a multi-tenancy situation. So I think this is for Atlassian. So they currently running this in their third-party Forge database. And then they have millions of tables. I think for that one, they moved from 750 Postgres clusters to 16 TiDB clusters or something like that. And then, yeah, of course, the numbers of tables are adding up.
So it's like instead of having all the users in one table and just partition the table.
Yeah. So each customer have its own set of databases and tables. So that's the multi-tenancy model they use. That have other things that we're addressing as well, like the optimizer, for example, should more or less see the same plans if the tables are similar and the data is similar. So sometimes you don't actually want to have full statistics for everything. You can actually accept to have the same plans because you know that this set of plans for this set of tables is usually quite good. So instead of having statistics for a newly added customer, for example, we don't have the statistics yet, or the data is very skewed because they're just starting using it, you can actually use a stable set of plans and apply them directly as well. And then we do have the version we're releasing now, TiDB X or TiDB 10 or whatever we will call it, where we're actually using an object store as the back store of the data. So as soon as we're done with an SSD file, we're moving it to the object store, and then we're reading it back from the object store to the other nodes. So instead of sharing data between the nodes, it actually goes through an object store. And especially in the cloud, S3, for example, Amazon's object store, it has very good bandwidth and so on. So it makes it very efficient as well, and also cost efficient, etc. And it's extremely durable as well. This also leads to, we can split other components to work directly with the object store. For example, I'm not sure if you're aware how an LSM tree works, but you normally compact files between layers and so on. We can do this also in more an offline setting, so we don't need to add that to the production serving nodes. We can do that on the side, and then they can just update their cache from it instead. And that means that we can do it once instead of 3 times, 1 per copy. So that basically means that if we will look at it from another perspective, where you would have TiDB nodes, TiKV nodes, possibly TiFlash nodes, and here we would actually use block storage. It goes more like a microservice architecture where we do have the object store as the main storage, and you can move out compaction, DDLs, analyze, and so on a bit. So the whole system is actually more flexible. It's easier to scale both in and out, and it's also much more efficient. So we've seen quite a lot of cost savings for our customers and so on when they're running this. Yes, I think there's one thing I missed there. So if you do have all the data already in S3 or an object store, that also means that backups is super fast, because you more or less just need to do a metadata snapshot. And then you can read out the state and all the files and so on as is already. And that's what I wanted to talk about. And yes, we're selling TiDB actually, and I hope you're selling ClickHouse as well. So we want to make money, right? Any questions?
For online schema changes, I was intrigued by the creation of the index. Are there any limitations on how many indexes can be created simultaneously with this approach?
Not really, I would say. It's not that I would say. I mean, there's implementation details and so on, of course, but we can more or less spin up more and more nodes to do them in parallel as well. And especially if you go then to the use where you have the object store, then it has even higher limits.
Can you talk a bit about the orchestration around creating indexes, like where you store the state of the individual index, how you spin up the infrastructure for it?
Yeah, so each table is like a metadata row, I would say, more or less, which has the current state. And we do have actually both per column and per index and so on, the actual state of it. Normally, everything would be just state public. But there you will see what state it is. And that means that if you have an SQL node that sees one schema version and another that might see the previous one or the previous one, then they would know how to process the index, if they need to write directly to the index, or if it even can read from it, etc. And we do have a queuing table more or less where we're adding the queued up DDLs. And there we also have some state tables for where they are in the backfill process, etc. So if a backfilling process would die, then we can just restart from a specific point in time, basically.
Like a specific microservice which watches that queue and then
Yeah.
spins up whatever it is.
Yeah. And we have the earlier version was more or less that just one TiDB node, one SQL node was the owner of this, so that was very simple. But nowadays it's just like you say that we have a distributed way, so we have more nodes that can pick directly from the queue and so on. Yeah.
So now you've entered the cloud era.
Yeah.
The elephant in the room, iceberg.
Yeah.
Do you think some of your stuff can be applied to basically when you would read or process with iceberg and the snapshots that they use to do the schema or things like that?
Most likely, yeah. I'm just, I'm worked more or less with transaction handling for most of my career, so the more analytic processing and so on, and how you evolve schemas and so on there, I'm not really aware how that's handled. So
iceberg in principle is actually a transaction.
Okay.
Right, and you say that you can read from the object store.
Yeah.
So it seems like a really interesting thing.
yeah, you should be able to apply the same thing there to if you want to have indexes there or add columns or change. Yeah.
Yeah, my question was about the object store. I'm more curious about the predictable performance. Like, let's say the P90 of S3 can be like 200 milliseconds, and it can vary, right, from P90 to 99.
Yeah.
So do you have any mechanism, like some kind of cache, discrete cache on top of it?
Yeah, so the storage node, the PyKV node especially, they are more or less reading things back from S3, so they are always serving from their local cache, basically. So it's more that we need to take into account the latencies when we have done a compaction, for example, or changing the some of the files. For example, when you ingested files for the DDLs and so on, we need to be aware that it might take slightly more time to update the caches for it. But the frontline serving, that should come from a local cache. And that also means that it's much easier to just use an NVMe and ephemeral disk instead, because even if the whole cluster would just be gone, you already have the actual data in S3.
I understand this correctly, right? You're calling it a cache now. So basically what's on the storage node is no longer the persistence layer. Everything is synced to S3 effectively. Okay.
Are you doing some pre-fetching, especially after compaction, where you know that most of the data we have is kind of stale?
Yeah, I think so. I actually don't. I'm not too aware of the exact implementation of that, but yeah, we should go directly into that. And since it's immutable files all the time, it's not really. You can more or less just exchange it, right? So we do have when we're moving the data ranges more or less, we do have a system for handling that as well. Yeah.